Oh, yeah, NYU, Stern.
Yeah, he got yesterday.
You got in yesterday?
Yeah.
Yeah, he got pulled off the list. And another person, do you know Eland? McElroy?
Where did you get in?
He also got off the wait list at NYU and he will be going there to the College of Liberal Arts. Or
Cool.
Pretty sure at least, he's doing the liberal arts track for like 2 years and then after that, he'll decide on the major.
Good for him. Okay, so we're going to back, oh, wait a minute, we're not there yet. We're not even there yet. There we are, okay. All right, so we're just gonna sort of jam through a little bit of graph stuff so that we can have it as a useful tool. Because ultimately what I would have liked to have done was said the second part was implement some sort of graph algorithm, okay, or graph structure. Because you can go in and you can build mazes, you can build, and actually, if you look at what AI actually is, AI ostensibly is a graph algorithm. Most AI is graph algorithms, right? Because if you, well, we're not quite there yet. So these are terms that we all know. We have like acyclic, right? And cyclic. What do those two things mean?
Like, it's like you know, can't go back.
In a cyclical graph, what can I do?
Go back to the original.
I can loop to the original one, right? Not just go back to it, but I can loop around to it. In an acyclical, I can't, right? So these are directed graphs. This is a directed. Once I get to B, I can't get back to A. I can go to D, but I can't make it back to C or A. Here, I could go from A to B to D to C to A. This isn't directed, so I can go back around. This one is also not directed, but it's not cyclical. Why?
Because it's like that, but you can't go back.
Yeah, it's one path, right? To make a cycle, I have to have more than one path. Like it's what, so what would we call this as well? Since there are no cycles in it. And what else is it?
One path.
So if there's only one path, a tree. It's a tree, right? As is that with the edge labels. Okay. More graph terminology. So we can talk about, we've got edges and vertices. It's saying that we've got, path of length 4. These are giving, it's kind of a little bit weird the way this is denoted. Vertex of degree 3. What do we think degree means with a vertex?
Number of vertices.
So there's 4 vertices. But this is a vertex of degree 3. We talk about degrees with a particular vertex.
Like how many connected there are actually?
Yeah, how many connections there are to other nodes. That's its degree. When they are connected like this, we say that they're connected components. So this is a connected component, this is a connected component, and this is connected components. That's pretty much it, right? And our graph definition is a set of vertices and a set of edges. Okay, vertices with an edge between them are adjacent. That's a term we'll see really frequently, right? So this vertice and this vertice are adjacent to each other. This one and this one are not. Okay, which becomes important when we start traversing our graphs. They may have labels or weights on them. And a path is a sequence of vertices connected by edges. Simple path is a path without repeated vertices. We're not going to worry about that one quite so much. And a cycle is a path whose first and last vertices are the same. Again, so if we go and we start here and we go here and then there, that's a mini cycle. There's a few of them in there. Cyclical and connected. All right, I'm going to skip through this. So what's our first thought when we see this? What structure do we think this looks like, first of all? Looks like a tree. Does look like a lot like a tree. Why is it not a tree?
This action.
Four things pointing to one thing. It's because like
It doesn't matter how many things are pointing to one thing. So we could just say that this node has 3 children. But group action, this is a cycle.
points to both.
It points right. You can go from group action to here, or from here to here. So since we have those 2 paths, it is that disqualifies it. Just like this, or just like, never mind. The BART map, right? Just had the one down at the airport. Okay, famous graph problems. I don't really want to delve into this one too much either. However, this one's actually super interesting. So is there a tour that you can take? Okay, we typically call them ST tours. In other words, from S to T. All right, we're going from S to T. Is there a tour that we can take that uses each node exactly once in the entire graph? Okay, that's one question. In this one, is that possible?
Yeah.
Each node in that entire graph.
Oh, in the entire graph?
Yeah.
Oh, no.
No, not in that one. Why? Where do we end up in trouble?
The tails.
The tail. Anytime I go out the tail, I'd have to come back,
Yeah.
right? And theoretically, if there's one tail, I might be able to figure it out, but there's more than one tail, in which case I have to traverse out and traverse back. Is there a tour that uses each edge exactly once? Okay, do these sound like the same problem? Or really, really similar?
Yeah, but.
Yeah.
But yes, like you can probably use edge tours because if you, oh, no. Actually. That would be the same issue because you, the tail.
I'm sorry, I'm not.
Or it would be the same issue as using each node.
With this particular graph, yeah, it would, right? So, okay, these are just, and I don't know why I skipped from this to that, from that to this. Some of the questions that we'll deal with graphs, can we make a path between S and T, just between nodes? Is there a path from S to T? Is there a path between all vertices? So are all of the nodes connected, right? If we come back to this, one, are all nodes connected? Yep, there's not like a station out here, right? That would defeat the purpose of a train station, right? If there was some station over here that wasn't connected to the rest of the network, that would be silly. Is there a vertex whose removal disconnects the graph? What does that look like? Well, that would be like if I had a whole bunch of.
If you get rid of the point, would you make it isolated?
Exactly. So if you have like one point and then a whole graph over here and then a whole graph over here, but everything connects just through that one spot.
Oh, it's like the root of a tree.
A root of two trees almost.
Oh,
Right, so you have all these things over here and all these things over here, and it comes through one point. Specifically, that becomes really problematic with. Anyone want to guess? Not function, but in the real world, where does that type of structure become super problematic?
Like highway?
So if we have one, yeah, highways would be a good point, right? If we have one, let's say that, let's say Pebble Beach had only one entry point instead of 5 or 6 or whatever it was.
Or just like,
Like the traffic. Yeah.
The traffic would be really bad.
okay, like an
When Monterey Peninsula became an island, right? That would also be really bad. Power networks. If you have power grids and you've got one station that connects 2 different sets of power grids, and that one station goes down, you got a lot of issues, right? So there's a whole bunch of different places where connectivity is actually like a bad thing, okay? Shortest path, where do we care about shortest paths in the real world? I'm thinking more in the real world. Yeah, I'm trying to go as fast as I can to my tennis game. I want the shortest path, right? Whether that's walking, and we all probably do it around campus too, right? What's the shortest way for me to get back to my dorm?
Yeah.
Okay, that's shortest path. Does it have any cycles? This is, again, sometimes important. So here's where these two that we were just talking about come into play. Euler-Tor, and this is Euler's, is there a cycle that uses every edge exactly once? And then a Hamilton-Tor, is there a cycle that uses every vertex exactly once? These sound really similar, yes?
They could be different though.
Yeah.
But how would they?
Could be different a little bit. Do we think they're going to be roughly the same to solve in terms of like figuring out how to solve them? They're not even close. And then we can talk about like, some of these are a little bit where planarity is, is it a 3-dimensional graph or a 2-dimensional graph? Isomorphism is, are there 2 different graphs that don't look at all like each other, but can you manipulate them into being essentially the same graph? Okay. But the Euler-Tor and the Hamilton-Tor are really kind of fun because the Euler-Tor, every edge, Hamilton-Tor, an efficient Euler-Tor algorithm, okay, is O of n, was found in 1873. Okay, 1873, they found an O of n Euler-Tor. What do we assume then is the Hamilton-Tor's efficiency?
Well, like,
Like every edge is like connecting the nodes, right?
Mhm.
Every vertex, that is a node, like we're calling a vertex like a node.
And it's a node, yeah.
It has to be open.
So if
But is
we're
it,
connecting all the edges.
Yeah.
With all of it,
And
So-
could it be more if you have to back? Or like if you go around in a loop and you come back and go the other way? Like, let's say you start here.
Right, I could touch a node and go a different direction out of the node, yeah, back out of the node. Well, I can't back out of the node though, right?
Where it's like, each vertex once, so it has to be.
What if you have like like two triangles on each side?
Okay,
And you start here,
Yeah.
go down.
Yeah.
Here, back at this one, across the bridge, down, down, down.
Yep.
there.
right, so you've just hit that node, yeah, okay, fair. So what do we think, O of N?
Wait.
I don't know.
It's not open.
It's not. So there is no efficient algorithm for the Hamilton Tour. If you came up with the efficient algorithm for the Hamilton Tour, you'd win $1 million and be on the cover of scientific magazines or mathematical magazines. No one's been able to do it. So they are exponential time. The best algorithms are exponential time. They seem like they're roughly the same problem, not even close. So O of N, is that efficient enough to actually run that algorithm
Yeah.
on a large data set? Absolutely. This is not. The Hamilton Tour has not been solved. It is one of the mathematical unsolved problems.
When was this like Hamilton Tour idea like?
Been around for a couple hundred years. Or 150 years, I guess, right? They've been talking about it probably for the same amount of time as they figured out the Euler Tour.
So it's probably not gonna be Tuesday's homework.
Have you guys ever heard the story of that? So,
The guy who solved like
he came to class late and there's two problems up on the board. He thought they were homework. So he went home and he solved them. And he came back and they were unsolved math problems. No one had ever solved them before. And he went home and solved them for homework because he thought he had to.
He rolled up to the classroom and on the chalkboard, there was two problems.
Right? Yeah, exactly. You're the professor who's been working on it for 20 years and the kid goes home and does it for homework.
He copied it, he thought it was he walked in late, it was on the chalkboard.
Yeah.
And he thought it was homework.
Yeah, it's a legit story.
I read, it's crazy.
Let's see, wait, let's see if I can,
What if we get
guy.
the exam, this problem about those.
Right. Solve, I don't think it's the Poincare conjecture. Solved,
Really famous math.
math, unsolved. I'm trying to figure out how to prompt this one. Unsolved math problem.
By being late.
Oops, yeah. Oops, unsolved math problem. Is that it? Yeah. Here we go. This is it. Yeah.
Yeah, at Berkeley.
Okay, he was late to graduate statistics class at UC Berkeley, mistook the problems on the board as homework. They were open problems that had stumped mathematicians for years. Late to class. The problems he solved were indeed famously unsolved statistical problems that had been challenging mathematicians for a while. So it's apparently it's not the actual math. Apparently the math in Good Will Hunting is not that high level, but it is like part of the inspiration behind it.
Awesome.
Isn't that kind of cool? I just think that's kind of a fun story. Yeah, I mean, and then you can see where different different graphs are going to make this could be easy or not. It actually comes from or it's related to this what's the name of the town? There's a town with 7 bridges, and the question is, can you cross every bridge exactly once and end up where you started? And the answer is no. No. It's a little town in Europe somewhere. I'll come up with it at some point, but not right this second. Okay. So graph problems are super interesting part of computer science. They're also really, really useful. Like we use them for, again, energy grids. We use them for obviously maps. We use them for social connections. So actually most when you start looking at social networks and stuff like that, it's all graph problems. Okay. So what we're going to do real quick is we're going to tackle connectivity. how do we want to go about traversing this graph to figure out whether or not S and T are connected? Algorithmically, what do we need to do?
We care the short, we want the shortest path.
We don't necessarily even need the shortest path yet. Ultimately, we will be interested in how to can figure out the shortest path.
Very, or like.
Okay.
On or off, like on being like, I have been here before.
Okay, so marking whether or not you've been to a given node?
Yeah.
Okay,
I'd probably go all the way to the right, then up, and then check if I can go to the right again. If I can't, then check if I can go to the left. If I can't, then go all the way down. Maybe.
well, remember the algorithm doesn't know right, left, and down. There is no right, there is no
Is it,
directional order in a graph.
How do you
I
reverse
think it's
it?
just like,
This thing's doubly linked.
Yes, we can assume that the connection is like both directions right now.
Okay.
So it's a what we call a non-directed graph, right? So doubly linked in a graph isn't the terminology we use. If it's non-directed, I could go either way. In a directed graph, I could, like, if there were little arrows here, I could only go one direction. Yeah, one-way streets ostensibly. So you actually bring up a really interesting point. We're not actually okay. If we come up with an algorithm for connected ST, what are we trying to actually like sort of figure out? If there's a path, right? So we need to go through like stepwise through this thing. Okay. So one possible way is to say, okay, does S equal T? Okay. If it does, we're done. Otherwise, we're going to check connected for any neighbor of V. I'm sorry, any neighbor V of S. So I'm going to say, okay, are you a neighbor of S?
Yes.
Are you equal to 7? Are you equal to T?
no,
Nope. So then where would I want to go?
The neighbors.
4 or 2. And so this is what you were talking about, like go left, go right. I have to decide how I'm going to break this tie between going to 4 or 2. Okay. For the most part, what we're going to do is just go to the smaller number. Right. So I go to a neighbor. But what's the actual first problem with this thing?
Have I been here before?
Yeah. So what's actually going to happen with this algorithm as it is?
Go back and forth.
Yeah, it's going to go from here to here, back to here. It's just going to keep doing this. It's in an infinite loop. So we do actually, we gonna put us one step ahead, which is we need to keep track of the marked things, right? So the first thing we're going to do is going to say, okay, we're going to do the same thing here, but we're going to say, okay, is S equal to T? Is 0 equal to 7? Nope, it's not. Okay. Whoops, that's not where we're going to be. We want to keep going.
We do the same thing we do with the map, like if we've been there, we put it in the map, so we don't have to.
You could, but this is simpler.
Oh.
Okay, because if we think about what marked is
Like, what's going on?
with neighbors, it's a great question. We'll hit it next class. Like how do we figure out who your neighbors are? Yes.
They have, well, 5 has 4 connections, 4 has 3 connections.
Yep.
And like,
How do you figure out who your neighbors are? Yep.
like, there's no like left or right or up or down.
Yes. Yeah. And so that is, it's not as hard as it's pretty simple, but you do need to keep track of those neighbors. And there's a couple different ways to do it that we'll look at. Okay. So what we're going to do is mark S, right? So we're going to say, hey, S, is S equal to T? So is 0 equal to 7? No, it's not. But the first thing we're going to do is we're going to mark S and say we've been here before.
What do you mean by market, like?
Well, so let's think about what would be a good way of marking S.
Boolean.
A Boolean. We're just going to say true. Like we're going to flip it to true. So what would I want to do with this whole graph? How would I keep track of them all? It's the simplest way to keep. If I know the length, how many nodes? What? It's an array. We're going to have an array of Booleans. It's going to be 9 things long, and so I'm just going to have 0, 1, 2, ... When I get started S, I'm going to say, okay, true, we've visited. Yeah.
Like, let's say you're on 5,
Mhm.
like, is it like an array list of nodes perhaps, and then you go through each and every single one. And then after that, you like pick one, maybe the smallest or no, like they have to be comparable, but like you go to the smallest one and then you go through those array lists, maybe?
We could do that. Yep. That is one way of doing it. So there's an adjacency list, which is what you're talking about, which is typically what we'll use. And there's an adjacency matrix that we're typically not going to use, but it's another way of doing it. So a matrix is like a 2D array. And an array list is essentially what you're talking about. Just keeping track of your neighbors, right? So what you'd ultimately do is the graphs get a little tricky because the first thing you have to do is build the graph. And that's when you're building the graph, you keep track of neighbors. And then when you go to traverse the graph, then you just say, hey, for one's neighbors, and you are pulling off that list.
Yeah, I just bring up, because I was thinking about the neighbor saying, I'm like, well, it's gonna be like a variable, I'm like, how do you make like a million different variables with like.
Right, and you don't know how many, right? How many, neighbors does one? Exactly. 5's got 4, so we need to have a variable length list that, yeah, exactly. Yep.
Okay, so, like, let's say we got to like, so we went from 0, 1, 4 to 3.
Yep.
But then that would mark 0, 1, and 4 all like marked.
Yep.
True. So then, would we be like stuck at 3 years?
Great question. Okay, so let's think about this, and this will explain itself as we go through. Okay. Okay, so we're going to visit each vertex at most once, right? We're not going to hit any vertex more than once, otherwise we get stuck in that infinite reverse. We're going to do this recursively, so that's going to answer your question. Okay. Let's see if this is what I want here. Okay, we'll do this one. Okay, so we mark 0. Is 0 7? Nope, it's not. So where do we go now? We go to the neighbor. We go to 1. Is 1 marked? First of all, no, it's not. So we go there. We first mark 1. We say we visited 1. And is 1 equal to 7? No, we're not there yet, right? So we check, is marked 0, because that's the smallest neighbor to 1. And it's already true. So we don't go there anymore. So now we say, okay, what's the smallest neighbor? We go to 2. Is it marked? Nope. We're going to go there. Is 2 equal to 7? Nope. Right. So we go to 2. We mark 2 as marked. Right. So we now have gone true, true. And we say, okay, 1 is already marked, so we don't go back there. We go to 5. Okay. 5 equal to 7. No, we check 2. It's been marked. Where do we go now?
4.
We go to 4 just because we've decided that we're going to go to the smallest next node. We could go to we could make other decisions there, but that's just, we decided that was our rule in our algorithm. Okay. I'm going to skip through a few of these because we're going to end up at 3. And this is Logan's issue. Like, now what do? We're stuck. We're on a little island somewhere. But this is a recursive algorithm. So what happens when we hit 3? We say, hey, is 3 equal to 7? No, it's not. Is 4 marked? Yeah. What do? We return. Where does return take us to? It just kicks us back to 4. And then 4 has got all the marked neighbors. Then I go to 5. Then where do I go? Now I still have a neighbor. Now I go to 6, right?
Smallest.
So what we're just trying to see, we're doing smallest neighbor, right? So now I go to 6. Okay, so we're backtracked to 6. Those are both false, right? Because they're not there. Then I check 6. 6 is unmarked. I go to 6. I say, is 6 equal to 7? Nope. Now I end up at 7. I mark 7. Is 7 7? Yes. Now this is the trick now. Do I go visit 8? Why not?
Because you already found it.
Yeah, my algorithm is done. I have true now as my return statement.
So 8, you just disregard it.
Because I went from S to T, I disregard 8. And what happens is, because it's recursive, I'm just going to backtrack through. So now I've got true between 6 and 7, and that's just going to carry back through the path. And you can actually see a little bit. I go to 2, I go to 1, I go to 0. And if you look at those trues, what do you see?
It's like the shortest.
It's the shortest path. In an in a non-weighted graph, okay, your connectivity will usually give you the shortest path. Now, have you visited every node? No, but you have the shortest path. Well, you have a path, first of all, from S to T. And in this case, it is the shortest path. Okay, and we kick all the way back to 0. And we say, yes, S is connected to T. Okay. Come on. All right. That's the demo. We don't need that. Whoa, wait a minute. Okay. Depth first traversal. We're just going to go real quick. So we saw it a second ago with Jackie's algorithm. So here we go through the entire subgraph before moving on to the next neighbor. This is depth first traversal or depth first search. So DFS is what you would normally hear this called as, DFS. So if I say that I'm going to go from S and go to try and find T with depth first traversal, what do I do first? What do I do?
All the way down.
Yeah, I'm going to go from 0 to 1 to 2 to 5 to 6. And then what?
Go back all the way up.
Yep, I just return. And then where do I go?
Down.
I go to 3 and then 8 and then I'm done. Okay, so I go, that's depth first traversal. When we talked about breadth first traversal, when we looked at the first graph filling algorithm, what would I do there, Donald?
You go level height.
Yeah, so I'd go 1, 3, 4, 7. Nope, it's not there. 2, nope, not there. 8, and I'm done. Okay, so there are times when depth first, when breadth, and we call that BFS, breadth first traversal. But depth first traversal, because again, you go as deep as possible. Where would I go if the 3 was connected to the 6? Or the 5, I guess in this case, connected to one of those two.
0, 1, 2, 5,
I go 0, 1, 2, 5,
6,
6, then to 3, and then to 8.
That's getting fast.
It is, yep. But I'm still going deep, right? Because I don't go back to 0. I'm going, and I'm just going still in the depth phase of that thing. Okay.
Is that, don't we even have that, because isn't that cyclical then?
Cyclical is fine with a graph, remember.
Oh,
If I go back to this one, what's the, it's almost, well, if I got rid of that, what is this thing? It's a tree, right? But this, we got one cycle here, and then we just throw in another cycle. It's no big deal because it's a graph. Cycles are totally fine. If, again, what are the two things that we're not really dealing with right now in terms of cycles? No, 2 paths from 1 to 2. I can't have parallel paths, and I can't have a loop in amongst one node to itself. Can't do those two things. Everything else is fair game ostensibly. Okay. Depth first paths. I think it's gonna look, we'll go do this one and then we'll call it a day. Whoops. What did I just do? Did I not? Let's try that again. Click. Okay, so this one is just, what this does is, this actually gives us a better sense of what the algorithm is actually going to look like. Okay, my other option is maybe I just make you build depth first search for the final. What do we think?
That's the one you showed us on that, like that map thing, the Jackie's one?
Yeah, pretty much. But it's much harder to do in processing because you have to keep track of 3 different arrays and everything else. If we think about what this thing does, right? What have I got here? Once I build the graph, what have I got? What's my structure? Yeah, but think about what I'm doing here. So I'm going to mark V, right? So if I call DFS on V, I'm going to mark V. Now, can I start from anywhere in the graph, theoretically? I can. I'm starting at S because I want to check whether or not S is, like I'm checking S and I'm going through and saying, hey, can I get from S to every vertex? Right? Can I get to everywhere in this thing? So I'm going to say, okay, I'm going to mark S. Well, S is 0, so this is going to change to true, right? And how do I get to, what's my connection? What's my neighbor? 1. How do I get to 1? From what? From 0, right? So I mark 0, I'm there. I check is marked 1. No, it's not. So I call edge 2. I say edge to 1 equals 0. And I call DFS on 1. no, they're already connected. You have to think about the fact that this is already structured. When you call DFS on a graph, the graph is already connected. You're not connecting them. You're saying, are they connected?
Oh.
Okay, because this. Idea what's going on.
0 and 1 are, so.
0 and 1 are connected. So I just say, how do I get to 1 from 0?
Okay.
Okay. Then I call DFS on 1, right? I mark 1 to true. And then I say, okay, is marked 0? Yes, it is. Is marked 2? Well, no, it's not marked. So what do I do there? I say, well, how do I get to 2? From 1. I change that. And then I call DFS on 2. And we'll go through in the same way we just did. Okay, we get to 3. When we hit 3, obviously we get a return statement. We get a return back to 5. Where do we go from 5?
Yeah. Are we still going?
We're still going depth, because think about what we're doing. When I hit, and I can show you sort of the difference between depth and so when I get to 1, what would breadth first search do here? Well, it could. So let's say now, what would it do? What would breadth first search do here? No.
It would go back to 1.
Yeah, it would go to 4. If you think about the levels that Donald was talking about before, we got level 0, level 1,
I'm thinking about it in the wrong direction.
level 2.
If you drink the levels, like how many steps?
How many steps away it is from that place starting vertex? Right? So this is all depth first search, because I go here, I go deep. Boom, that's depth. But then I just have to back out, just like we did in that maze, right? So I back out, then I go to 6, oops. Then I go to 7, again, depth. And then I back out, I can go to 8, and then I just return all the way through. Okay? So you'll notice a couple of things. When I get done, what do I see here? All true. And let's say, how did I get to 6? Well, I go to 6. I got to 6 from 5. How did I get to 5? From 2. How did I get from 2? From 1. How did I get to 1? From 0.
Oh, so you can find the shortest path.
Well, I can find every path.
Oh, yeah.
I can find a path now to every node, and I can say this is the path to every node. And you'll see the order of depth first returns here, right? Order of DFS calls. I go from 0, then I call 1, 2, 5, 4, 3, 6, 7, 8. Okay. The order of returns from my depth first search is different. Because where's my first return statement as I go through this thing?
Yeah, like.
Yeah, so what's my first one? 3. Then what? Yeah, so if you think about the way we went through it, right? I go here, I get to 3. 3 is the first place where I have no neighbors to check. So 3, then 4, 7. You return when there's no neighbors to go visit, when I can't go any deeper, and I have to back up.
Oh, and since you already checked 5.
So I was at 5, I have neighbors. So 4 didn't have neighbors to check. So I return 3, then 4. I get to 5, I have neighbors to check, so I have to go to 6. Then I go to 7. Now 7 doesn't have any neighbors, so now I add 7.
Then 6.
Then 6. Whoops, I'm going the wrong direction.
5
6, 5. Well, now I go to 8. Now I return 8, 5. Or sorry, I return 8. Then I return 5. Then where? 2, 1, 0. Okay. How is that useful? That's a good question. We're not quite there yet. Okay. But how am I going to structure this thing? What do I need to make this work? 2 arrays, a marked and an edge 2. And I've got this function that calls DFS. And as I go through this, I'm just filling in my 2 arrays. That's essentially it. Now that I'm simplifying it a little bit, but that will be the algorithm that we use when we actually implement this thing. Okay, and that's depth first paths, tree versus graph versus go away again. Okay, and just to find, I'm going to fill this in really quick and then we're going to call it a day. We talked about our pre-order, in-order, post-order, and level order traversals for our trees, yes? Want to go over that? Are we good? Sweet. So you have the same thing with graph searches almost. We have a depth first pre-order, we have a depth first post-order, and we have a ostensibly level order. Okay, we have 3 of them. So our pre-order is we do something before DFS gets called, which is what we just did. So what would our depth first search pre-order be on this graph? If we think about like a print statement, well, if we're not printing, what are we doing? So what do I do what's the first thing I do?
We'll check if it's 7.
I check if it is, and what do I do when I'm here?
Mark the one.
I mark it. So that's my sort of, if we think about our pre-order, it's just marking the nodes. Okay. So when we do that, what's our first thing that we do? What's the order of our depth first search pre-order? What's the order of it?
0.
Yep. 0, 1, 2, 5, 4, 3, 6, 7, 8. Okay. What would our depth first search post order be?
Would it be returning when you have no neighbors?
Yes, it's that one.
So
So it's, when we get there, it's the 3, 4, 7, 6, 8, 5, 2, 1, 0. That one. Now, why is that useful? We'll look at why it's useful because it's a good question. Yeah, Logan.
I don't get
It's the returns from the recursive call,
Oh,
right? So our pre-order is like, what do we mark and then move on? Right? Just like with our pre-order here, the pre-order here was we marked our node and then moved on to the next one, right? So we get D, B, and then A, and then C, we mark and then move on, right? So in our depth first pre-order for this thing, we mark and then we move on, and then we mark and we move on. That's our depth first search pre-order. Our depth first search post order is the returns from the recursive call. Okay. And we'll talk about sort of what use that has. In a minute. So it does go to the tails first. It goes to the points where that don't have neighbors first. But it's got real world like uses as well. Okay. So our last one is breadth first search, right? So our level order, like when we did this, we did D and then BF and then A, C, E, G. Well, again, we're going to do the same idea here. So what is the breadth first search return order on this thing?
0.
Try and write, let's write it down. So 0 is first, obviously. Then what? We know it's 1. So I'm going to break up the levels here. All right, so we get 0 is its own level. And then 1. And then what?
2. Then 4.
No. So if you think about it, it's 0 and then 1. Is 2 alone? No. What level, what else should be on that level? 3? Nope.
5.
It's what is 1 connected to?
2 and 4.
So think about breadth first search is going to go and grab every neighbor.
But isn't it all about perspective? Like you can.
No,
Really? Because you could like.
Nope.
Go 0 to.
because what is 1 connected to? What are 1's neighbors?
0, 2 and
2 and 4. Does it matter the order?
They're the same distance.
They're the same distance. It doesn't matter the order. So from there, what's the next level? Because you know, you got to think about like this connects to here because I'm starting at S. It doesn't matter where I start. Okay. But beyond where I start, this has 1 neighbor. 1 has 2 neighbors. We go visit 1's neighbors next.
Then it would be
That's
3.
what-
Now it gets a little tricky because I have to go look at all of 2 and 4's neighbors.
Would you go by the least amount of neighbors first?
No, well, we could make like algorithmically, we could make decisions that way. but we don't really care. So 2 and 4 are their own level, and then what?
3.
Nope, not 3. Sorry, yes, 3. So
Five.
3 and
5.
5, and it doesn't really matter how I get there, because I've got 2's neighbor is 5, 4's neighbor is 3 and 5, right? So now I've gone from here, right, to here. What are my neighbors now?
8 and 6.
Yep, 8 and 6,
Then 7.
and then 7.
So you're going by like how far away they are. from
How
you.
many steps away from the start, we don't call it the root anymore, the starting vertex. Right, it's just how many steps away do we have to take? Okay, and that's breadth first search, BFS. Okay, so 0, 1, 2 and 4 together, 5 and 3, 6 and 8 and 7. Okay, we're gonna do that next class. There's your homework. Figure out a general algorithm, okay, to do that,
So isn't the.
to do a breadth first search. So we've got this graph, right? It's the same one we've been working on. Find the length of the shortest path from S to all other vertices. Okay, this is BFS. You're creating BFS, right? You need to somehow visit vertices in BFS order, because we've done depth first search, right? That's what we did a second ago, is did depth first search. Use some kind of data structure. Do not use recursion. You do not want to do this recursively. You just don't. Okay. That's your homework. Questions? And I hate to spray this all at you again in the last like 4 days of class and just do lecture. However, again, it's really important that you all have some general sense of graphs before you come out of this class. So we got a little behind in this class, and so that's why I'm trying to catch up. So again, for our final project, and you can start to give this some thought, you're either going to create a full lesson plan, you're going to, actually, I think I'm gonna do that differently, unless you really want to have, unless you have like a something for implementing some sort of cool data structure in some practical way, like processing, building something like that. I think what we're gonna end up doing is implementing some sort of graph search. Because I have the, that is a project that we did last year. So I think that's what I'll have you all do.
So lesson plan and graph search or?
No, one or the other. So you're on that final day, you'll present either some sort of lesson plan.
Oh, we get to pick?
You guys pick.
What do you mean by lesson? Like,
So so you're a little bit late. So you're going to create, so you're like, I tell you, you got to come back next year to this class, whoever's in this class next year, and teach one of the classes on any topic of your choice.
oh,
Presentation, you can have hands-on stuff, you can use cards, you can do whatever you want to. You're gonna teach a lesson on whatever you want to teach.
like 15 minutes or?
No, like 40 minutes, obviously you're not gonna do the whole teaching,
Oh,
but I want you to lay out like what you would do, have the slides for it, like you're gonna create a lesson plan for a 40-50 minute class.
okay.
Does that make sense?
Yeah.
Cool. So give a little thought to this and you can start on that. Have an awesome weekend. Yes, sorry.
So, yeah, research, so like.
This is breadth first search. So this piece is you're doing a breadth first search order. You're trying to figure out the algorithm for, so we sort of see
Is it the one that we?
that's depth first search.
Right.
So depth first search is you're going, right? We go from 0 to 1 to 4. Actually, this is a different structure, isn't it? Right? So we go from 0 to 1 to 4 to 3 to 2 to 5 to 6 to 7. That would be depth first search. Breadth first search is going to do what?
0.
Go to 0.
1 thing.
1 to 3,
2, 4.
2, 4,
7, 5.
5 and 7, and then 6. So you got to think about how you would
Doesn't
do that.
Just the same thing as a training level? The sideways training.
sort of, but there's more like we have cyclical connections. Yep. So you can assume that the tree is constructed. And sort of the background pieces of information that you have. So our preconditions are The tree's constructed and you know your neighbors.
Oh,
You can call on your neighbors.
well, we don't have to find, like, I don't have to like see. I don't have to like, okay, so I know.
Well, you gotta think through, because it was pretty easy when we said, hey, I'm gonna go here, then what's my next smallest neighbor? That was depth first search, so that's kind of simple. How am I gonna go from here to here, right? But then come back and go over here without recursion.
Make up this story.
You start at S, and you're trying to find the shortest path to every other vertex.
I was thinking if like 30. That'd be any.
Nope, you're starting at 0 and you're trying to find the shortest path.